So today I'm gonna finish this course, Intro to Reinforcement Learning, and I've decided that after I'm finished with this, I wasn't sure what I was gonna do on stream, but I think I'm gonna start learning C++ and have as a goal to try to build my own AI library with C++, maybe using TensorFlow's lower API, maybe just trying to build it from scratch without using any APIs. Because I think it's a good goal to have because I want to increase my understanding of AI and the way that things work behind the scenes. And I also want to have more flexibility to maybe create my own models in the future instead of being trapped by the ones we have today. But I understand it's a very difficult goal, so I'm not sure if I will be able to achieve it or not. If I think I would be able to achieve it with enough time, but I'm not sure if I'm gonna stop in the middle of it to maybe deviate to another goal instead. So we'll see about that. And then on the side of stream, we're gonna practice these things that I already know with some projects that I'm doing on my own that I don't necessarily want to put on stream. So let's start the thing. Previous tutorial, you learned how to build an agent with one step look ahead. This agent performs reasonably well, but definitely still has room for improvement. For instance, consider the potential moves in the figure below. Note that we use zero-based numbering for the columns, so the leftmost column corresponds to call equals 0. Next column corresponds to call equals 1, and so on. With one step look ahead, the red player picks one of column 5 or 6, each with 50% probability. But column 5 is clearly a bad move, as it lets the opponent win the game in only one more turn. Unfortunately, the agent doesn't know this because it can only look one move into the future. This tutorial will use the Minimax algorithm to help the agent look farther into the future and make better informed decisions. Minimax. We like to leverage information from deeper in the game tree. For now, assume we work with a depth tree. This way, when deciding its move, the agent considers all possible game boards that can result from one, the agent's move, the opponent's move, and the agent's next move. We work with a visual example. For simplicity, we assume that at each turn, both the agent and the opponent have only 2 possible moves. Each of the blue rectangles in the figure below corresponds to a different game board. So agent move, opponent's move, and is looking 3 steps into the future. We have labeled each of the leaf nodes at the bottom of the tree with the score from the heuristic. We use made-up scores in the figure. In the code, we use the same heuristic from the previous tutorial. As before, the current game board is at the top of the figure, and the agent's goal is to end up with a score that's as high as possible. But notice that the agent no longer has complete control over its score. If the agent makes its move, the opponent selects its own move. And the opponent's selections can prove disastrous for the agent in particular. If the agent chooses the left branch, the opponent can force the score -1. If the agent chooses the right band, the opponent can force the score +10. So the best choices here are bad for the next step. Take the time now to check this in the figure to make sure it makes sense to you. With this in mind, we might argue that the right branch is the better choice for the agent, since it is the less risky option. Sure, it gives up the possibility of getting the large score that can only be accessed on the left branch, but it also guarantees that the agent gets at least +10 points. This is the main idea behind the Minimax algorithm. The agent chooses moves to get a score that is as high as possible, and assumes the opponent will counterattack this by choosing moves to force the score to be as low as possible. So pretty much Nash equilibrium. It's trying to achieve the Nash equilibrium. Which basically Nash equilibrium is just a strategy that makes all the decisions of your opponent irrelevant to your decisions, meaning that they can't make any decision that is going to make your strategy worse. So that doesn't mean that your strategy is great and it's going to win. It just means that they can't make any decisions that are going to make the strategy worse. So as with other strategies, you might have a bigger score, but if the opponent changes their strategy, then your strategy might become worse. That is, the agent and the opponent have opposing goals, and we assume the opponent plays alternately. So in practice, how does the agent use this assumption to select a move? We illustrate the agent's thought process in the figure below. Agent plans to select move that maximizes score. Assume opponent plans to select move that minimizes score. Agent selects move that maximizes score. So it's making the assumption on the next game portion of game tree, and then reassigning the values of the first, probably. The example Minimax assigns the move on the left score of -1. And the move on the right is assigned a score of +10. So the agent will select the move on the right. Yeah, -1, +10. We will use several functions from the previous tutorial. These are defined in the hidden code cell below. So it's the functions from the previous two tutorials. Every function forget heuristic, check if window satisfies heuristic condition. Rename this piece config. And I was having trouble understanding these loops here. I think each loop is looping through the whole grid by rows and columns. First row, then column. But I'm not sure. This structure here, what makes them different? I don't understand really well. We also need to slightly modify the heuristic from the previous tutorial, since the opponent is now able to modify the game board. Particularly, we need to check if the opponent has won the game by playing a disc. The new heuristic looks at each group of 4 adjacent locations in a horizontal, vertical, or diagonal line and assigns 1 million points if the agent has 4 discs in a row, the agent won. 1 point if the agent filled 3 spots, the remaining spot is empty, the agent wins if it fills the next spot. -100 if the opponent filled 3 spots and the remaining spot is empty. -10,000, the opponent has 4 discs in a row, the opponent won. This is defined in the code cell below. think the reason why it's confusing is because this this function calls the other functions. So it's kind of hard to follow what's going on. On the grid's passed here as an argument. I think it's just counting the number of windows that are available, number of empty spots. Yeah, so this counts the window for 3 and 4 pieces. And then here counts for the opponent. Score equals number of trees minus calculation there. Next code cell, we define a few additional functions that we'll need for the Minimax agent. Uses Minimax to calculate value of dropping piece in selected column. So it's calling this function drop piece with the arguments. Minimax is just apparently from a library. Upper function for Minimax, check if agent or opponent has 4 in a row in the window. Let's see the drop piece again. It's a copy of the grid, loops through the rows. I think what this means is that I'm not sure because it's the same value here and here. I was gonna say that it loops from this value to this value based on these steps, but not sure if that makes sense. So where was I? Upper function for Minimax checks if game has ended. list grid 0, not count 0 equals 0. Check for a win, horizontal, vertical, or diagonal. For a row in range, config rows. Column in range, config. Minus config in a row, -1. Window equals list, grid, row, column plus config in a row. This terminal window config, turn true. So it's interesting that here is minus and here is plus. Oh no, it's plus. I was looking at the wrong thing. But here it doesn't have the argument. Here it has the argument. Oh, it's the other way around. So I think that this is the portion that I'm having problem understanding. Because I don't remember really well what in a row is. I think it's the number that is on a row, the number of pieces, but I'm not sure. Minimax implementation, def minimax. Also, it is defined here. No def, maximizing player, mark config. This terminal equals terminal node config. Valid moves. So this checks if it is a finishing move. Finished state in the board. C for C in range config columns if nodes 0 C equals 0. So this creates the list of valid moves in the columns. If node 0 C equals 0. So C is the column, 0 is the row. So just checking for the next valid move. If depth equals 0, I use terminal, return get heuristic, node mark config. Depth equals 0 or terminal. Maximizing player value equals minus np dot inf. I don't know what's this. Probably some numpy function. Then here's choosing the maximum value. But it's calling the function again. Is recursive somehow? Oh yes, because it has to check for depth 3. So it's recursive because each time it's checking for the next, I think. Assume that's going on. But it doesn't have a stop thing here. So assume it goes on until it reaches the maximum amount of valid moves. Because for column, invalid moves. For column, invalid moves. Child, drop piece, non-call mark. So here does the same loop, but for the opponent. You won't describe the Minimax implementation in detail, but if you want to read more technical pseudocode, here's the description from Wikipedia. Function Minimax, no depth, maximizing player. Is if depth is a thermal node, then return the heuristic value of node. Maximizing player has maximizing player, then value equal minus infinity. What? This is confusing. This part. Oh, I think is the value. Is assigning the value. The value of a move to minus infinity, but for each child of node, the value, max value. Oh, so it's assigning minus infinity in case it doesn't find the maximum, the best move. Just say that if a move is not the maximum is gonna be minus infinity. I think I got it now. Max value, min max child, depth, false, return value. So it's pretty much replacing it, doing this so you can replace each move that it finds with the value that it's supposed to have based on the heuristics. Where is it? Oh, so np infinite inf is just an umpire function probably that gets the infinite value. Here's negative and here's positive. For each child of node, the value was main value min max, and then here does the opposite to find the worst moves for the opponent. Finally, we implement the Minimax agent in the competition format. The end steps variable is used to set the depth of the tree. Depth agent. So valid moves again. Convert the bar chart to the grid. I think the reason why it's difficult for me to understand this is because for some reason it's really hard for me to focus on things that I don't really care about. So I don't care about this game, and then it becomes difficult to because you have to spend a bunch of energy trying to understand how the game works and stuff. And I think I didn't pay attention on the first two tutorials. So it has this cascade effect of you don't understand something really well in the beginning and then it translates to all the rest. Repeat dot as array best bar reshape config rows config columns scores dictionary of the zip valid moves and score move. Score move I think is the function defined here somewhere. Yeah, here. To get the score. Call invalid moves. So it's looping through the valid moves and applying this function at n steps. This function gets the minimax, which is this one here. So it does that function to call this function to call the other function. I don't understand why here's n steps and here's n steps minus 1. Yeah, but I think it's a little bit more clear now than it was when I started, although it's still somewhat confusing. So zip, I'm not really sure how it works, but I think is a, from what I've seen from stuff before I did the Kaggle courses, it's like a multiplication between, is used to multiply vectors or matrices. So I probably should look this up. The zip function returns a zip object, which is an iterator of tuples where the first item is in each past iterator is paired together. Then the second item is in each past iterator are paired together. The past iterators have different lengths. The iterator with the least items decides the length of the new iterator. So they don't show what happens here. I think it's putting the things together, which it's kind of difficult to understand. Also, it's making a list, a tuple with both tuples. Oh no, yeah. The first item of each one becomes one item of the bigger tuple. And I assume we can do this with lists as well. Python zip method takes iterable or containers and returns a single iterator object, having mapped values from all the containers. It is used to map the similar index of multiple containers so that they can be used just using a single entity. So here it has the output. It's interesting that here makes an object, and then in the other example it makes a tuple. Yeah, it's assigning each one with the corresponding element in the index. You can get it now. So where did I stop here? Oh, I think I stopped here. Finally, we implement the Minimax agent in the competition format. Then stats variable is used to set the depth of the tree. I stopped here. By the moves, grid, score, yeah, score is equals dict, zip. So it's gonna pair the valid moves with the score in this list, which is gonna be all the scores for valid moves based on the function. Get a list of columns moves that maximize the heuristic. key for key scores, dot key scores key equals max scores dot value. So just getting the maximum scores and putting it through this. Select it random from the maximizing columns. Next code cell, we see the outcome of one game round against a random agent. Agent random render. And we check how we can expect it to perform on average. I think I'll put this here. These sites here are the sites I'm gonna use to learn C++ in the beginning at least. And I think this one is paid. I'm not sure, so I'll have to see. I've got win percentage, agent 1, agent 2, and rounds 100. So there's 6 rows, 7 columns in a row for. So maybe that's the reason why when it's looping from horizontal is making minus the inner row thing. Yeah, I'm still not sure about that. Agent 1 goes first, roughly half the time. Agent 2 goes first, roughly half the time. Get me percentages. So it's 100% against a random agent. The research for the tutorial looks at all groups of or adjacent grid locations on the same row, column, or diagonal and assigns points for each occurrence of the following patterns. I think I get it now. So it's making the loop on each one and counting how many times in order to assign a score. Is it really necessary to use so many numbers to define the heuristic? Consider simplifying it as in the image below. Yeah, so how would each heuristic score the potential moves in the example below? Where in this case, the agent looks only one step ahead. Each heuristic will lead to the agent selecting the better move. So it only selects one step ahead. So, but which one is the agent? Red or yellow? I think it's red. Yeah, it's red. Because it's only red here, the third one. So it would obviously be true to prevent the other one from. It would be column true, yeah. With one step look ahead. First heuristic is guaranteed to select column 2 to block the opponents from winning. The second heuristic selects either column 2 or column 3. No, so the first where it selects each with 50% probability. As for this game board, the first heuristic is better. In general, you can expect that the first heuristic is a better heuristic, since you cannot trust the second heuristic to block the opponents from winning. I'm not sure if I really got it, but whatever. Count the leaves. In the tutorial, we worked with a small game tree. Agents move, opponents move, and actions next move. The game tree above has 8 leaf nodes that appear at the bottom of the tree. Definition leaf nodes in a game tree are nodes that don't have nodes below them. In the Connect X competition, the game trees will be much larger. To see this, consider a Minimax agent that is trying to plan its first move, where all columns in the game board are empty. Say the agent builds a game tree with depth tree. How many leaf nodes are in the game tree? User answer to fill in the blank below. It is trying to plan its first move. Where all columns in the board game. So it's obviously gonna be a mathematical multiplication of the probability of all board states. Because each play can lead to another play, but I don't feel like doing the math. Say the agent builds a game tree of depth tree, how many? Well, it's gonna be the probability of the first three stamps. Oh yeah, there's also draws and winning times. So you would have to get the probability of each of them drawing, each of them winning, and of neither winning, and then sum all of them. It's probably how you find out. Which move would the engine select? This question you check your understanding of the min-max. I They don't have explanation here, so which is a shame. Which move would the agent select? In this question, we'll check your understanding of the min-max algorithm. Remember that with this algorithm, the agent chooses moves to get a score that is as high as possible, and it assumes the opponent will counteract this by choosing moves to force the score to be as low as possible. Consider the toy example below of a game tree that the agent will use to select its next move. Which move the agent select? User answer to set the value of the selected move variable below. This should be of 1, 2, or 3. So I have to think which move the agent's gonna select. And these are the heuristics that is assigning for this move. So the way that I think you should think about this is get the heuristics and see how many chips there are for each heuristic, and then figure out which one is gonna lead to the uh, which one the opponent would choose based on that, the all possibilities. But I also don't feel like doing that. So I'm just gonna like look at the answer. Let's see the hints. See if they say anything interesting. Yeah. Examine the assumptions. The min-max agent assumes that its opponent plays optimally. With respect to the heuristic, and using a game tree of limited depth, this is almost never the case. In practice, it's far more likely for the agent to encounter a suboptimal, that is, worse than optimal opponent. Say the min-max agent encounters a suboptimal opponent. Should we expect the min-max agent to still play the game well, despite the contradiction with its assumptions? If so, why? I think the answer is yes, because it's gonna recalculate on the next steps which move is the best. Yeah, I think the answer is yes. You can still expect the min-max agent to perform well. On a high level, assuming an optimal opponent simply overestimates the opponent does not break the algorithm. The effect of overestimating the opponent is merely that the min-max agent will take longer to win than if it had a more accurate understanding of its opponent. Yes, it's pretty much Nash equilibrium. For instance, the min-max agent is highly unlikely to select the same column 3 times in its first 3 moves, since it assumes an optimal opponent that will certainly block the winning play in the next move. But it is not a bad initial strategy for playing against an agent that selects columns completely at random. Submit to the competition. Now it's time to submit an agent to the competition. Use the next code cell to define an agent. You see an example of how to write a valid agent in this note. If you decide to use the Minimax code from the tutorial, you might like to add alpha beta pruning to decrease the computational time. Get the Minimax algorithm to run much faster. In this case, alpha and beta to refer to true values that are maintained while the algorithm is running. They help to identify early stopping conditions. Without alpha beta pruning, Minimax evaluates each lift node. With alpha beta pruning, Minimax only evaluates nodes that provide information that affects the agent's choice of action. Put another way, it identifies nodes that could not possibly affect the final result and avoids evaluating them. So now I should do all the code. So it's pretty much all the other things, the other functions from the tutorial. Yeah, I'm definitely not gonna be able to do this without looking at it, at the code. I think if I don't look at it, I'm just gonna get stuck here because I don't understand really well. I know that I have to loop in 4 different ways, 3 different ways, horizontal, diagonal. Maybe I should do that first thing. But I don't remember where the functions go. I don't know if all of the functions go inside the agent. I think it has to be like that, maybe. So remember there's a piece, drop piece function. I'm just gonna make a copy of the grid. I don't remember if that's how it works. Then I don't remember really well. I think valid moves. I don't remember. Then remember there's the horizontal loop and then the row in range config dot rows config in a row -1. Maybe it wasn't like this. Maybe this was the one that was -1 here. Strictly going based off memory, not understanding, which is obviously bad. Config.call, I think, instead of columns. Then there was something with the window count that I also don't remember really well. Windows, oh, window.count, and then you call some stuff. I'm just trying to write as much as I can of the stuff that I think I remember correctly. Because I still don't understand really well how it works. I think I got the concepts down, but the code just maybe if I took more time in the beginning to understand, I would be able to understand now. But then the diagonal, I think there was positive diagonal and negative diagonal as well. And I think I should do in a row -1 as well here. I'm gonna look at the tutorial for the rest. But here is different. So maybe this one. Yeah, so all the functions have drop piece, check when you move. Also just drop piece, check when you move. So Dev drop is dev jack. But I think that that agent doesn't perform the look ahead thing. This end steps look ahead. This one. So it's next grid. Yeah, I knew there was something off about making like this, but and here is the config rows -1 -1. And his rows as well. So probably config calls. Next grid row call break equals 0 break. So if it's a spot that is not I don't understand why equals zeros because to me it's 0 when you don't have any piece there. So it should be the other way around. Next grid row call space. Also didn't put the arguments there. I don't think, at least for me personally, and I obviously could be being biased here, but I don't think this was a good course to learn how it works. But I'm not sure if they could do a better job. I'm not really sure. Or if there's other courses out there that are better. Because I feel like the only way that I'm probably gonna learn is by actually doing a project instead of doing these courses. Maybe the course is a good introduction to get yourself familiar with the things, but I don't feel like I've learned how to do it on my own. Like how to think about it. Conceptually, yes, but how to think about it in terms of coding, I'm still confused about it. I think the main point of confusion is how to select the flow of information, like which stuff I'm gonna do first, what function I have to think about it first, and how, because once you have the, and not even once you have the total vision, like it's kind, that's the hardest part. part, I think, about this. Because when you start thinking about functions that connect to other functions, then it becomes very complicated to think about which one you're gonna do and how that one is gonna call the other ones, the logic of the whole thing. Now comes the so this goes inside this function here. I'm just gonna move this to the other monitor, honestly. Just a lot easier to copy. So I was here. So this horizontal part, I got it wrong because it did minus one thing. The other one is config columns minus window equals list. Another thing that I'm not sure how to practice is how to use different functions than the ones you know. Because usually, if you're a beginner, you're just gonna default, like I'm doing now most of the time when I'm doing stuff on my own, just defaulting to the stuff I know already, instead of trying to think about different ways that I could do it, do something better. Because you just don't know when is a good time to search on, and you can just use stuff you know. For example, this list like this, I'll never do stuff like this. Window.count piece config in a row. I also don't understand where this count comes from. Maybe it's a method from the list. So it is a method. It's probably just counts the amount of times something shows up in the list. how many times the object occurs in the list. So I stopped here. Then I also did the loop the wrong way for vertical. And they are all row and column. Loop through the row first and then the columns. This one seems to be different, so I'm gonna copy it by hand manually. I think the last one I'm just gonna copy this straight away. The return false is from the function, not from the loop. None of them returns true, then it's gonna return false by default. Like doing stuff like this, not be the first thing that comes to my mind if I was doing this on my own. If I was doing the whole project, I was probably gonna research a bunch, and then I would probably go would build, would build a list and make some sort of loop, I think. But outside of this, so this next calls next grid. Now next grid's sign here is gonna call drop piece, which is the other function. So just don't understand here. Like it's passing the range as an argument. So maybe that's something that I definitely don't never used it and I don't understand it really well. Maybe that's something from Python you can do in Python. So instead of passing the rows, it's passing the range of row config. And it's not passing piece and config. Then variables, false. But I think this is still not making the, yeah, this is definitely not making the look ahead thing. So I have to look at this one. Shouldn't my agent be a class instead of a function? Also here the agent is outside of the other functions. So maybe I should do this one. I'm gonna do it like they did on this tutorial. Oh, but that it's weird because it says your code here and it's below that my agents. So I think what I'm gonna do is just copy all these functions inside of that agent. Get heuristic. So I think all of these need to be indented properly. Yeah, now it seems to be correct. And now I copy this stuff here. Oops. This should be here as well. And maybe that's what they want me to do. Line 18 doesn't have any line here. Row arrange config rows. So it's definitely not the first part, I think. So I did this manually. So that should be somewhere here. Oh, it says line 18, so it might be the first one. Maybe that's the problem. Inspect OS. I'm not gonna submit this, I think. So I think I understand the concepts well, but I don't understand the code very well. And I think it's a good introduction. There's still one more tutorial to go. Good introduction, but I'll probably need to I think if I do something that I'm interested on, like creating a chess, uh, reinforcement learning agent, I think I will learn a lot more about it. Or maybe a poker one. But I'm not sure if I'm gonna do that. Another thing that I'm not sure about and I'm kind of thinking is I've learned so much stuff that I'm kind of confused by which one to choose for which situation, which technique, which stuff. So I think that's another thing that I have to think about. Uh, how do we know if we're gonna use reinforcement learning or classification, regression, all the other stuff? I think that's the hardest part I found about this so far is it's not so much necessarily the models, it's the variables, all the other variables that go is like the problem itself, not the model. The data source, how to convert the data source into a trainable thing, how to make sense of it, how to structure and think about the way that you're gonna put things together. Not so much the libraries or even the math about it. So far, our agents have relied on detailed information about how to play the game. The heuristic really provides a lot of guidance about how to select moves. This tutorial will learn how to use reinforcement learning to build an intelligent agent without use of a heuristic. Instead, we will gradually refine the agent's strategy over time, simply by playing the game and trying to maximize the winning rate. This notebook we won't be able to explore the complex field in detail, but you'll learn about the big picture and explore code that you can use to train your own agent. Neural networks. It is difficult to come up with a perfect heuristic. Improving the heuristic generally entails playing the game many times to determine specific cases where the agent could have made better choices, and it can provide challenging and it can prove challenging to interpret what exactly is going on wrong, and ultimately to fix old mistakes without accidentally introducing new ones. Wouldn't it be much better if we had a more systematic way of improving the agent with gameplay experience? This tutorial towards this goal will replace the heuristic with a neural network. The network accepts the current part as input, and it outputs a probability for each possible move. Yeah, so the other thing is that I'm not sure how the previous tutorials relate to the network, neural networks. I don't think I've seen anything that it is a neural, yeah, that's back propagation and that stuff. There is the minimax function, but it's not quite the same thing. The network accepts the current part as input and it outputs a probability for each possible move. 0% probability 0, 0, 0. Then the agent selects a move by sampling from these probabilities. For instance, for the game board in the image above, the agent selects column 4 with 50% probability. This way, to encode a good gameplay strategy, we need only amend the weights of the network so that for every possible game board, it assigns higher probabilities to better moves. At least in theory, that's our goal. In practice, we won't actually check if that's the case, since remember that Connect 4 has over 4 trillion possible game boards set up. How can... Yeah, another thing that is going through my mind when I'm reading this is the Monte Carlo search tree and those techniques to decrease the size of the tree so you can simplify the game and find small Nash equilibrium solutions that become the bigger one. They converge over time. Setup. How can we approach the task of amending the weights of the network in practice? Here's the approach we'll take in this lesson. After each move, we give the agent a reward that tells it how well it did. If the agent wins the game in that move, we give it a reward of +1. Also, if the agent plays an invalid move, which ends the game, we give it a reward of -10. Also, if the opponent wins the game in its next move, the agent fails to prevent its opponent from winning, we give the agent a reward of -1. Else, the agent gets a reward of 1 divided by 42. At the end of each game, the agent adds up its reward. We refer to the sum of rewards as the agent's cumulative reward. For instance, if the game lasted 8 moves, each player played 4 times, and the agent ultimately won, then its cumulative reward is 3 times 1 divided by 42 plus 1. If the game lasted 11 moves and the opponent went first, so the agent played 5 times and the opponent won its final move, then the agent's cumulative reward is 4 times 1 divided by 42 minus 1. Ends in a draw, 21 moves, reward 21 times 142. 7 moves. Selecting an invalid move, the agent gets a cumulative reward of. Our goal is to find the weights of the neural network that, on average, maximize the agent's cumulative reward. This idea of using reward to track the performance of an agent is acquired in the field of reinforcement learning. Once we define the problem in this way, we can use any variety of reinforcement learning algorithms to produce an agent. Reinforcement learning. There are many different reinforcement learning algorithms such as DKO and HUC and PPO, among others. All of these algorithms use a similar process to produce an agent. Initially, the weights are set to random values. As the agent plays the game, the algorithm continually tries out new values for the weights to see how the cumulative reward is affected. On average, over time, after playing many games, we get a good idea of how the weights affect cumulative rewards. The algorithms settles towards weights that perform better. Of course, we have glossed over the details here. There's a lot of complexity involved in this process. For now, we focus on the big picture. This way, we end up with an agent that tries to win the game. So it gets the final reward of +1 and avoids the -1 and -10. And tries to make the game last as long as possible, so that it collects the 142 bonus as many times as it can. You might argue that it doesn't really make sense to want the game to last as long as possible. This might result in a very inefficient agent that doesn't play obvious winning moves early in the gameplay. And your intuition would be correct. This will make the agent take longer to play a winning move. The reason we include the 142 bonus is to help the algorithm you use to converge better. Further discussions outside of the scope of this course, but you can learn more by reading about the temporal credit assignment problem, reward shaping. The next session, we'll use the proximal policy optimization algorithm to create an agent. Yeah, so it starts to get really complex once you have memory, once you need to put memory so that it learns from past experience. Then it gets really confusing, at least on the Brilliant course. That's what I found. Code. There are a lot of great implementations of reinforcement learning algorithms online. In this course, we use stable baselines. Currently, stable baselines is not yet compatible with TensorFlow 2, so we begin by downgrading to TensorFlow 1. There's a bit of extra work. Oh, let me see here. So just does pip install TensorFlow with an exclamation mark before. There's a bit of extra work that we need to do to make the environment compatible with stable baselines. For this, we define the connect_var gem class below. This class implements connectX as an OpenAI gem environment and uses several methods. Reset will be called at the beginning of every game. It returns the starting game board as a 2D NumPy array with 6 rows and 7 columns. Change reward customizes the rewards that the agent receives. The competition already has its own system for rewards that are used to rank the agents. And this method changes the value to match the reward system we designed. Step is used to play the agent's choice of action, spy this action, along with the opponent's response. It returns the resulting game board as a NumPy array. The agent's reward from the most recent move only one of +1 -10 as well, and whether or not the game has ended. If the game has ended, then it equals true, otherwise then it equals false. To learn more about how to define environments, check out the documentation here. I think I can close this using custom environments. I need to get more experience with writing classes as well. Something I haven't practiced a lot, so check here that your environment follows the gene interface. So this is the documentation of the library stable baselines. I'm not gonna read this now. So this is the function. So class, I should say. Self agent true random. KS make connect x debug equals true. Self.env self.row self.columns. So assume env stands for environment, maybe. Self.actions space dot discrete self.columns. Self-observation spaces dot box. Double corresponding to the min-max possible rewards. Stable baseline throws error if these are not defined. Turn in p.array soft OBS board, reshape. Def change reward, self, what reward done. If old reward equals 1, the agent won the game. If it's not, -1. The opponent won the game. Else returns 1 divided by 42. Then soft step, def step, self action. Check if agent's move is valid. Self.obs board int action equals 0. If it's valid, play the move. Self.obs, all the reward done. Self.env step. Yeah, the only thing I don't understand really well here is this env thing here. Because here is KSI, KSI, KS underline name equals make, not a, and don't say a describe it, describe it anywhere in the code. So let me try to search for this. So it is a way to get data from another model, apparently. Though I'm not quite sure still. Loading environment of football failed, no module named gfootball. gfootball. This notebook will train an agent to beat the random agent. We specify this opponent in the agent true argument below. Create connect for environment. Also here is the env equals connect for gym. Oh, but then it doesn't make sense. And for gym agent true. So just creating a class, an object of this class. And assigning which will env. Stable baseline requires us to work with vectorized environments. For this, we can use the dummy vecenv class. The monitor class lets us watch how the agent performance gradually improves as it plays more and more games. Vectorized environments are a method for stacking multiple independent environments into a single environment. Instead of training an RLL agent on one environment per step, it allows us to train it on n environments per step. Because of this, actions passed to the environment are now a vector of dimensions n. It is the same for observation rewards and end of episode signals. In the case of non-array observation spaces such as dict or tuple, where different subspaces may have different shapes, the sub-observations are vectors of dimension n. Multiprocessing. Abstract as asynchronous vectorized environment. Not sure if I really understand well, but so app gets update, get install, this stuff here. PortOS. Create directory for logging training information. Logging progress, monitor it, log there. Log directory, allow early results. True. Create a vectorized environment. So there's a lot here that I have to research and understand better. Next steps to specify the architecture of the neural network. In this case, we use a convolutional neural network. To learn more about how to specify architectures with stable baselines, check out the documentation here. Note that this is the neural network that outputs the probabilities of selecting each column. Since we use the PPO algorithm, PPO1 in the code cell below, our network will also output some additional information, called the value of the input. This is outside the scope of this course, but you can learn more by reading about actors critic networks. Your network for predicting action values. So uses df.nn is a TensorFlow function method, you could say. Not exactly sure what it does, but dot relu. Assume it's gonna create a tensor with relu as activation. Layer 1 active conv scale the images C1 and filters 32, filter size 3, stride 1, in scale np square root 2 qargs. Layer 2 active conv, so it's creating two layers of convolutional networks. Conv 2 FC, I'm not sure what this does. Return active linear layer 2 and hidden class custom policy. Need super custom policy soft init args qargs CNN extractor. Let's modify CNN. Initialize agent. Model equals pp1. Custom CNN policy vacant verbose equals 0. Yeah, there's a lot here. There's a lot going on. The code cell above, the weights of the neural networks are initially set to random values. In the next code cell, we train the agent, which is just another way of saying that we find weights of the neural network that are likely to result in the agent selecting good moves. We plot a rolling average of the cumulative reward that the agent received during training. As evidenced by the increasing function, the agent gradually learned to perform better by playing the game. Model.learn, total timestamps. Then just put in the file that is saved the training process before. And plotting on the graph. Finally, we specify the trained agent in the format required for the competition. Check selected column is valid. It's valid. Bars. Not select random move. Next code cell, we see the outcome of one game round against a random agent. And we calculate how it performs on average against the random agent. So this is the same function that I was used before in the other tutorials. So 83%, which is worse, funny enough, than the previous tutorial. It's important to note that the agent that we've created here was only trained to beat the random agent. because of its gameplay experience as being with the random agent as opponent. If you want to produce an agent that reliably performs better than many other agents, you have to expose our agent to these other agents during training. To learn more about how to do this, you can read about self-play. Custom policy network. Stable Baselines provides default policy networks for image and other types of input features. One way of customizing the policy network architecture is to pass arguments when creating the model, using policy keywords parameter. You can also easily define a custom architecture for the policy. I think I'm gonna make this favorites because eventually I might need that. Competitive self-play. We found that self-play allows simulated AI to discover physical skills like tackling, ducking, faking, kicking, catching, dive for the ball without explicitly designing an environment with these skills in mind. Self-play ensures that the environment is always the right difficulty for an AI to improve. Thinking alongside our Dota 2 self-play results, we have increasing confidence that self-play will be a core part of powerful AI systems in the future. So this is from OpenAI. OpenAI. God, have have difficulty saying some words for some reason. Overfitting. Ranges were overfitting by co-learning policies that were precisely tailored to counter specific opponents, would fail when facing new ones with different characteristics. Dealt with this by pitting each agent against several different opponents rather than just one. Possible opponents come from an ensemble of policies that were trained in parallel, as well as policies from earlier in the training process. Given this diversity of opponents, agents needed to learn general strategy and not just one's targeted to a specific opponent. I don't think I'm gonna save this because I know about OpenAI, so I can remember in case I want to research that. Furthermore, this is a very quick and high-level introduction to reinforcement learning. If you'd like to dig more deeply into this topic, I recommend checking out the following free resources: David Silver's videos, Richard's textbooks, Tennis Kids Repository Bootcamp. Great. So they have more resources here. Yeah, so it talks about Monte Carlo here. Yeah, I think the backpropagation and classification, linear regression, this kind of stuff, it's kind of easy to understand. But once you start getting to this point, I think then it starts getting very complex, very fast. I don't think I'm gonna keep. I think I'm gonna keep track of this GitHub. The parallel bootcamp. Intro. Sample. And this seems to be a bunch of videos only. Just good, but
admin just to outline what this course is about, particularly for those of you who are actually doing this for credit. And I know that's probably about half of the audience here. There's a few people.
I'm probably gonna watch this later. Then maybe open these videos. I wonder if they have it on a playlist so it's easier.
Hi, good morning, everyone.
There's just so much
Thanks for
stuff
coming
to learn.
out.
It's kind of crazy. Probably. Oh, shit. It's 4 years old. So let me see where I stopped. And assume this is gonna be a book or a paper. I think this is stuff that I'm gonna study when I'm more comfortable with the easier parts. So I can build up from there. Because although I understand the concepts, my technical skills in coding are lagging behind. So it's better to become comfortable translating the concepts into code on the easier stuff first. Trying to build a library of on C++ with C++ from the scratch. Then once I really understand, or when I feel like I really understand how to build it, then I can move to this more advanced stuff. Oh, I think a great idea is to save this and put it on Discord for later. This is pretty much a book, basically. I'm gonna save this and put on the Discord. Maybe I'll share this link as well. Put this link there so I remember it. Yeah, I'm gonna put this stuff on this Discord so there's not too many tabs open. Continue to check your understanding. Roll call. So set the architecture. In the tutorial, we learned one way to design a neural network that can select moves and connect for. Neural network had an output layer with 7 nodes, one for each column in the game board. Say now you wanted to create a neural network that can play chess. How many nodes you would put in the output layer? Option A, 2 nodes, number of game players. Should be 16 nodes, number of game pieces. Each player starts with, to see 4,600 nodes. Number of possible moves, 64 nodes, number of squares on the game board. Use your answer to set the value of the best option variable below. Your answer should be, okay, so let's think about this. So if I understand correctly, this works with the heuristics. No, this is not with the heuristics. It's gonna learn by playing itself. Against the random agent. thing is that I don't understand this code really well. They didn't explain the parts of the thing. There's so many parts here that I feel like I have no clue what it means. I kind of have an idea, but don't really understand it. Like, I don't know what is considered to be the output layer here. Maybe it's the rewards. So for the most recent move, only one off. So it's the rewards for each move. I think the outputs are the rewards for each move. Because that's gonna be used to determine the cost function. Oh, it is, yeah, it is the cost function. So it should be number of possible moves, maybe. See? Yeah, it should be like this. What? Use your answer as the best option variable. Your answer should be one of. So maybe it's option A they want. Option. Correct. Use a similar network as the indicator. The network should output a probability for each possible move. What doesn't make sense to me is that there isn't just, well, but yeah, it's only looking one move ahead to determine, not the whole game size. Decide reward. In the tutorial, learn how to give your agent a reward that encourages it to win games of Connect 4. Consider now training an agent to win at the game Minesweeper. Go to the game to clear the board without detonating any bombs. To play the game in Google search, click on the play button at this link. Oh, this. Oh no, what have I done? Fuck, I think I just deleted the cell by mistake. What do I do now? May reload, see. Yeah. Hopefully it comes back. No, it still didn't work. Yeah, I don't know what to do now. Because I just look at the solution. Here's a possible solution. After each move, we give the agent a reward that tells it how well it did. If agent wins the game that move, it gets a reward of +1. Else, if the agent selects an invalid move, it gets a reward of -10, -1. Yeah. To check the validity of your answer, note that the reward of selecting an invalid move and for detonating a mine should both be negative. The reward for winning the game should be positive. The reward for clearing a square with no hidden mine should be either 0 or slightly positive. So I wonder how the reward for chess would be. If it's based on all possible moves, the number of possible moves, how do you classify which move is good and which move it isn't? Maybe it would be if you hang a piece, you lose, but it gets really complicated. Amend the code. In this next part of the exercise, we will amend the code from the tutorial to experiment with creating your own agents. There are a lot of hyperparameters involved with specifying a reinforcement learning agent, and you have a chance to amend them to see how performance is affected. First, we need to make sure that your Kaggle notebook is set up to run the code. Begin by looking at the settings menu to the right of your notebook. Your menu will look like one of the following. Your internet settings appear as required for verification. Click on this link. This will bring you to a new window, then follow the instructions to verify your account. After following this step, your internet settings will appear off. Once your internet settings appears off, click to turn it on. Begin by running the code saw below. So this is the code that it was done in the tutorials. Yeah, blah blah blah. Run next the code cell below to train agents with PPO and review how the rewards evolve during training. This code is identical to the code from the tutorial. We try total. So maybe I should do the internet thing before I run this cell. So I don't think I'm gonna do this part. If trained well, the plot which shows average cumulative rewards should increase over time. However, we have verified that the code runs by try making amendments to see if you can get increased performance. I like to change PPO. So this, yeah, just giving a bunch of ideas to change the code. Yeah, so it's just an introduction. I feel like I'm very far off from being able to apply this by myself without looking at any libraries or any stuff like that. Just wait for it to save. I'm not sure if I'm gonna start this today. I have a bunch of stuff that I want to do off stream. takes too long, I'm not gonna save this. Okay. Yeah, okay, that's it. If I don't come back today, later, I will probably come back tomorrow or some other time. So, see ya.